The topic for today is non-Cartesian tensors. So let me write it down here. It is non-Cartesian tensors. Non-Cartesian tensors. Yeah. Let me non-Cartesian tensors. Okay. So in our earlier classes, we discussed about Cartesian tensors. And while discussing Cartesian tensors, we considered only the behavior of the rectangular components of tensors under orthogonal transformations of Cartesian coordinates. Okay. We discuss only Cartesian coordinates, and we discuss how the components of the tensor change when we rotate the Cartesian tensors. Now, let us generalize this idea. Now, in non-Cartesian tensors, we are going to include any change of variables. It is not restricted to Cartesian coordinate system. Okay, as an example, let us look at the spherical coordinate system. So let me discuss one example here. As an example, let us consider a spherical coordinate system, and the spherical coordinates are r, theta, and phi. Okay, r, theta, and phi. And what is the relation between r, theta, phi of the spherical polar coordinate system and the xyz of the Cartesian coordinate system? They are related by this equation: x equal to r sine theta cos phi. And y equal to r sine theta sine phi. And z is given by r cos theta. Okay, and we can see here that this is not a linear transformation. Okay, this is not a linear transformation. And earlier we wrote something like x prime, y prime, z prime. We wrote something like this. This was a11, a12, a13, a21, a22, a23, a31, a32, a33 times x, y, z. Okay. This is a linear transformation. How do we know? Because here x prime is equal to a11x plus a12y plus a13z. Okay, so x prime is a linear combination of x, y, and z. So this is simply a linear transformation. But if you look closely here, these are not linear transformations. Okay, this include non-linear terms like sine theta, cos phi, a linear equation or the relation between the differentials. Okay, here x, y, z, and r theta phi are not related by a linear equation, but if we consider their differentials, then we can we shall obtain a linear relationship. Let us see. So if you look at this first equation, what would be dx? Dx would be this dr times sine theta cos phi plus, now we keep r constant, r, then the differential of sine theta is cos theta d theta cos phi, and then we keep r and theta constant and vary phi. So we have r sine theta sine phi. So this, the differential of cos phi is actually minus sine phi. Okay, so here we instead of this plus sign, we'll have a minus sign here. So Let me erase the plus sign and replace it with a minus sign. Okay. Okay, good. So I replace this with a minus sign. Minus sine phi d phi. So this is the relation between dx, dr, d theta, d phi. Similarly, we see that dy is equal to dr sine theta sine phi. Okay, so we have kept theta and phi constant and differentiated r. Next, we keep r and phi constant and take the differential of sine phi. So it would be r cos theta d theta sine phi plus, then we keep r and theta constant, and then we take the differential of phi. This would be r sine theta cos phi d phi. So this is dy, and what is dz? Dz would be, from here we can see that it is dr cos theta plus, okay, here again we'll have a minus sign because the differential of cos theta would be minus sine theta. So I'll erase this plus, we'll have a minus sign here. So dr cos theta minus r sine theta d theta. Okay, so now if we look at the differentials, so let me change the color here. If we look at the differential, we have dr here, we have d theta here, then we have d phi here, we have dx here. So we can write it in a matrix form. Let it be dx, dy, dz. In matrix form, this is equal to, what is the first term here? The first term is sine theta cos phi. What is the next term here? This is r cos theta sine phi. What is the last term here? This is minus r sine theta sine phi. And similarly, for a second line, we have here sine theta sine
Sir,
phi.
password dia.
Yes.
Kamu owner.
Oh, this is sine j.
হয়.
Sorry. This sign, this is not exactly sign, this is cos. Okay, thank you for the correction. So let me erase this. Okay. This is cos phi. Okay, cos phi. So minus r sine phi, sine theta sine phi. Then we have sine theta sine phi. Then we have r cos theta sine phi. Then we have r sine theta cos phi. And for the last line, what do we have? We have cos theta. Okay, we have minus r sine theta and 0. Right? This is dr d theta d phi. Okay. So here we see that, say the x, y, z. Let me use the spotlight now. So here you see that x, y, z and r theta phi. They relation, the relation between them is non-linear. But if we consider the differentials of the coordinates, dx, dy, dz, dr, d theta, d phi, then we can still see that the differentials are related by a linear relationship like this. Okay, so this is how the differentials of dr, d theta, d phi, they transform to dx, dy, dz. or in other words, you can say the differences dx, dy, dz, they transform to dr, d theta, d phi through this relation. Okay, so let me go to the next page. Where is the next page? Okay, it is here. Next new page. Okay, so let me change my sheet also. So let us look at another example. Yeah. Let me change it here. Okay, let us look at another example. Example 2. Example 2. So let us consider general coordinates. Some general coordinates x1, x2, and x3. This is one set of coordinates x1, x2, x3, and another set of coordinates x1 prime, x2 prime, x3 prime. If we are given a relationship between this set of coordinates, between this first set of coordinates and this second set of coordinates, if we are given a relationship between these coordinates, like what we just saw in the earlier case, let me go back to my previous slide. Yeah. Here we have this relation. We have this relation between them, xyz and r theta phi. If we have some a relationship of this form, like this form, so in this case also, if we are given a relationship between x1, x2, x3, and x1 prime, x2 prime, and x3 prime, then we can write the relations between the two sets of differentials as follows. Say, for example, let me write it here. Say, for example, x1 prime. This, we write it as x1 prime is some function of x1, x2, x3. Okay. Then x2 prime is again some function of x1, x2, x3. Similarly, x3 prime is again some function of x1, x2, x3. See, if we have something like this, then we can find a relationship between the differentials of x1, x2, x3, and dx1, dx2, dx3. Okay, so let us write down the differential of dx1 prime. So the differential of the x1 prime is here. We see that x1 prime is a function of x1, x2, and x3. And from the theory of partial derivatives, we can see that this is very simple. Dx1 prime by, sorry, dou x1 prime by dou x1 multiplied by dx1 plus dou x1 prime by dou x2 dx2 plus dou x1 prime by dou x3 dx3. Okay. Similarly, we have for the x2 prime, this is dou x2 prime by dou x1 dx1 plus dou x2 prime by dou x2 dx2 plus dou x2 prime by dou x3 dx3. And also for x3 prime, the x3 prime, this is dou x3 prime by dou x1 dx1 plus dou x3 prime by dou x2 dx2 plus dou x3 prime by dou x3 dx3. Okay, so this is the relationship between the differentials of x prime and x. Okay, we can write it in a simple matrix form like we did earlier. So let me write it here. So it would be the x1 prime, the x2 prime, the x3 prime. This is equal to, one moment, let me Let me take this out. Okay. Now this is equal to so this one, this and this, they will form the first row. So this will be dou x1 prime by dou x1, dou x1 prime by dou x2, dou x1 prime by dou x3. This is the first row. The second row would be dou x2 prime by dou x1, dou x2 prime by dou x2, dou x3, dou x2 prime by dou x3. Similarly, the last line would be dou x3 prime by, yeah, I don't know whether it is still visible to you or not. Let me so let me write it like this: dou x3 prime by dou x1, then dou x3 prime by dou x2, dou x3 prime by dou x3 multiplied by dx1, dx2, dx3. So what have we done here? We have written this three set of equations. We have written this three set of equations in matrix form. Okay. Now let us try to write these three equations by using the summation convention and index notation. I repeat, let us try to write these three equations by using the index notation and summation convention. So let's do it. So this we can, let me change the color. Okay. This we can write it like this. This implies, what is this? This can be written as dxi prime. Dxi prime is equal to dou x, let me write it here like this, dou xi prime. Okay. Oh, let me erase this. Okay, and let me write it here. It is dx I prime is equal to dou x I prime divided by dou xj multiplied by dxj. Okay, so this is what we have here. Dxi prime equal to dou xi prime by dou xj dxj. So when I prime is equal to 1, we have this relationship. Okay, and what is the repeated index here? You can see that the repeated index here is j. Okay, is j. So that means j has been summed over. So for if you take I equal to 1, then it will give you the first equation. So dou x1 prime by dou x1 dx1 plus dou x1 prime by dou x2 dx2 plus dou x1 prime by dx3 dou x3 dx3. So we get the first equation. And if I equal to 2, we get the second set of equations. Second set of equation. And if I equal to 3, we get the third equation. Okay, so let me pause the recording here.